get started. Today we are going to look at chapter 6, section 3. This is about conditional probability and the intersection of two events. The conditional probability of event F given an event E is written as the number of outcomes in the event F intersection E over the number of outcomes of the event E. So this is equivalent to write down the probability of the intersection event F and E over the probability of E. So you could use, either way to do the problem. You could use the little n formula with the conditional or the probability with the conditional. So we will look at one by one. Okay. So let's move to the first example. Let W be the event that a randomly chosen person drinks 64 ounces of water per day. Let V be the event that the randomly chosen person has a varicose veins. And let Z be the event that a randomly chosen person has kidney stone. So typically here we are given three events, right? Okay, now the first part is given that the person drinks 64 ounces of water per day. So this is the given, the condition events, right? But the question is, write the probability, right, for what? That the randomly chosen person has a varicose vein. So this is kind of, they are asking us to find the probability of the chosen person has a varicose vein. So the probability of V, but we already have the condition, right? So whatever we have the event followed by given is my conditional event. So in this case, this event is W. The probability we are looking for the event which is those who have a varicose vein. So this is my, the target event. So that is basically the probability of V given the event W. So I apologize for the second answer. There's a typo that is not correct actually. The probability that a randomly chosen person has a kidney stone. Now this is the one we are interested, finding the probability those who have a kidney stone. So this is going to be my event C, right? But the given condition was, the given event was he or she has a varicose vein. So this is the given event. Therefore, the probability of Z given V is the correct answer. Now look at the next one. The next one is, suppose we randomly pick a figure from the set below. So we are given basically 1, 2, 3, 4, 5, 6, 7 objects here. We are choosing one at random. First one is find the probability of choosing a circle. The given event is which are solid. So it is conditionally given probability. So the probability of circle given solid is I'm using the little n formula, right? So here let me explain something here. Example A. So the probability of choosing a circle object given the condition is which is solid. So that means here you are given two events. Say this is my event F. Say this is my event E. Formula says that the probability of event F over E is little n F intersection E over n of E. The number of objects or outcomes in the set F intersection E. What is F intersection E? The circle with solid. So if you look here, circle with the solid, I have one such an object. Therefore, it is just one, right? Over the number of objects in event E. Event E is here, choosing a solid object. So if you look at here picture, there are three of them. So that is 3. So technically speaking, the probability of circle choose given solid means what? You are given only the condition solid pictures. Among all three solids, the question is what is the probability of choosing circle? So among three objects, obviously I see only one circle picture, therefore it is 1 out of 3. So that's the meaning. So now let's move to the part B. Finding the probability of a square object. The given condition is this is now solid. Again, I'm using the same formula. This is F and this is E. So this is NF intersection E over NE, right? So now the number of objects in F intersection E. That means what? That means we are looking for the event, choosing objects which is square with a solid. How many square with solid? Square with solid. There are two of them. Over n of e. The event E is now choosing solid. Again, I have 1, 2, 3. There are 3. So it is 2/3. So the next one. The probability of choosing a solid object, the given condition is now, which is a square. So this is my event F and this is E. So again, let me write down one more time about the formula. So now this is the number of objects in solid with the square. So the solid with the square is just 2 over. Now my event is the choosing objects which are squares. How many squares we are choosing? 1, 2, 3, 4. There are 4 of them. So it is 2/4. If you simplify, this is 1/2, right? So every time whenever you find the numerator and denominator, so you have to treat like a separate, problems and find one by one. So I'm finding, each possibilities from my sample space. So always we have to look at the sample space for the, problem. Okay, right. So the next one, number 2. We are drawing a single card from a standard deck. Find the following probabilities. First one, the probability of choosing king given that it is heart. So this is my event F, this is E. So NF intersection E over NE. Okay, now let's look at my numerator. Number of outcomes in F intersection E. So you are choosing a card that is king with a heart. So we will find only such a one card in heart pack, right? King with heart. Now what is N of E? The number of hearts. You will see 13 of them in card pack. So it is 1/13. And B, now the probability of choosing heart given condition is that is a king, right? So now here, this is F and this is E. So F intersection E over NE. Now here, heart with king. Again, we have only one such a card, but my E is now choosing king. So how many king cards are there in the card pack? You will see 4. There are 4 of them. So it is 1/4. Okay, the next one. The probability of choosing number 7, but the given condition is that should be a face card. Right? So this is F and this is E. So that is F intersection E over NE. Now I'm looking for a card that is a 7 with face. Do you see such a card in card pack? Card with the number 7 and face? No, there's no such a card, right? So it is an impossible event. You don't see such a card. So therefore, the outcomes from empty set is 0 over the number of outcomes from event E, which is the face cats. There are 12 of them. So that is 0 over 12, which is 0. So that is number 2. Number 3. Number 3 says we are rolling a single die. So I apologize for these answers. These are not correct. So let me do again here. So we are rolling a single die. Remember, the sample space for the single die rolling is 1, 2, 3, 4, and 5, 6. The first part is what is the probability of getting even number. The given event is which is less than 5. So this is event F, this is event E. So that is N if intersection E over NE, right? So now, what is F intersection E? You are choosing a number which is even and less than 5. So look at this event in your sample space. So what are the possibilities or outcomes you have? You are choosing a number that is an even but should be less than 5. Of course, I have only 2 options, right? 2 and 4. Therefore, this is just 2 over E. Event E is less than 5. How many less than 5 outcomes I have here? Number which are less than 5. There are 4 outcomes, right? So it is 4. So 2 over 4, that is 1/2. Okay. Part B, finding the probability of a number which is less than 5, but the given condition is that should be an even number. Okay, it is F, C, so N F intersection E over NA. Okay, so let's find first the numerator, the number of outcomes, the number which is less than 5 and even. Of course, there are 2 of them, but the denominator is NE, the number of outcomes. You are choosing an even number. How many events number there are in my sample space? 1, 2, 3. There are 3 even numbers. Therefore, NE is 3. Okay. So the choosing number less than 5 and even, the condition is even, there is a two-thirds. Okay. Now let's move to word problems. So if you look at number 4, in a certain retirement home, 45% of the residents play poker. You see now, this is kind of, the number which is given in percentage. So this is the probability now, right? What is the probability of, the persons from the residents, they play poker? It is 45%, right? So that is simply the probability of those who play, the poker game. So whenever you see the percentage in the problem, it is nothing but a probability. So let me convert, the word problems in symbolic way. So the probability of playing poker game is 45%. That means the probability of play poker game is now 45%, which is 0.45, right? Okay, what is next one? 55% are gardening. Therefore, people, the probability of doing gardening is 55%. That is 0.55, right? Okay, the next one is this. And 20% go to gym. The probability of go to gym is 20%. That is 0.2. It is also known that 15% of them play poker and go to gym. Okay, so the 15% of the people, they do both, right? Play poker and go to gym. So that is 15 percentage. That is 0.15. One more number is there. What is that? 35 percentage of play poker and doing gardening. So they play poker and gardening, right? So that is 35 percentage. That is all the probabilities I have now. Okay. Now let's move to the question part then. Question is, if a random resident is selected, find the following probabilities. The first part is, what is the probability, right? Those who play poker, but given that he or she is gardening. So you see the way I'm writing. So I'm just writing in symbolic way, the given conditional probability, right? Okay, now this is my event F, this is my event E. Now I am going to use the probability formula for the conditional because all the information pieces are given in probability. So I'm going to use, instead of little n, I'm using probability. The probability of event F given event E is nothing but the probability of the intersection event F and E over the probability of event E, right? Okay, so I'm using that. So what is this? This numerator in terms of the given problem. The probability of F intersection E, so that means the playing poker and gardening that I have here. The playing poker and gardening probability is 0.35 over the probability of E is gardening. What is the probability of gardening? It is there, second one, right? Probability of gardening is 0.55. So take your calculator and simplify this. This will give you how much? 7 over 11. So I'm not rounding up my answer. I'm keeping as an exact answer. So we always do that, right? Unless they are used to round up, otherwise keep in fraction. The second part is find the probability those go to gym but play poker. So those go to gym, but the given condition is play poker. Now again it is a conditional, so this is F and this is E. I'm using now probability formula. So now go to gym and playing poker is my numerator. So go to gym and playing poker. Oh, it is there. Playing poker and go to gym. It is 0.15 over probability of E is playing poker. So where's that? It's at the top. The playing poker is 0.45. So if you simplify this, this is just one term. Okay. Okay. The next one, number 5. What is that? Given that the probability of a student spending time for watching TV is 0.89, the probability of students spending time for the reading is 0.44, and the probability of a student spending time for reading and watching TV is 0.11. What's the probability of a student spending time reading given that the student spending time watching? So the question is finding the probability of reading given that he or she is watching TV, right? So my event F is now spending time on reading, and my event E is spending time on watching TV. So again, it is a conditional probability. So I'm using my conditional formula, right? Okay. So the probability of F and E the probability of reading and watching, so doing two things, right? What is that probability? Probability of reading and watching TV is 0.211. It is 0.11 over the probability of eventually watching TV. The probability of watching TV. Do you know that? Yes, it is 0.89, which is 0.89. Okay, so then simplify this. That is 11 over 89. That's the probability of reading given that he is watching TV. Okay, so I'm leaving number 6 for you guys. Why don't you try number 6? So you are given a table here now. Make use of this table as an information chat and try to find out these two you know, questions. If you feel any difficulty, please let me know. Okay. Now let's move to the next definition. Next definition is about finding the probability of intersection events, two events. Okay, when the probabilities of PE, PF, and the conditional probabilities are known, sorry, the probability of the intersection of two events E and F, right, can be calculated by using these two formulas. You see me? I have two formulas here. The first one is finding the probability of E intersection F, but this formula is valid if E and F are independent events. Okay, independent. The second formula again for intersection events. This formula is true when E and F are the dependent. Okay, so here E and F are dependent events. So we have two cases. So you have to read the problem carefully and identify which formula is supposed to be used. Okay. So the first formula says that the probability of E intersection F is nothing but the product of two probabilities of E event and event F. The second formula says that the probability of E intersection F is the product of the probability of event E and the conditional probability of F, right, given on E. So these are the two formulas we are going to use to find intersection, probabilities. So let's look at these problems now. Okay, number 7. We are drawing two cards now with replacements from the standard deck. Find the probability that both are kings. Okay, so let me explain one thing. Now here, you are drawing two cards, right, with replacement. When you, replace the card, right, the probability of, the drawing second card will not be affected by the first one, right? Because you are anyway replacing the cards and whatever you have at the beginning is going to be there for the second time drawing also. So if we have such a situation, we call those events as independent events, right? For example, tossing two coins. You are tossing two coins, right? So at the same time, simultaneously, you are tossing two coins, right? The outcome of the second one will not affect the first one, right? Vice versa, because you are doing two different things. So if you have certain events or those kind of events are called the independent events. Okay. So now we are replacing two cards, replacing cards and drawing two. Therefore, it is an independent event. So with replacement is always independent. So that means what? That means I'm going to use my first formula, right? The question is now finding the probability of both are kings. So sorry for that. So both are king. So that means what? That means your first drawing is king and the second also king, right? Basically, we have now two events. This is my event E. This is my event F. Remember, these two events are now independent events. Therefore, finding N, the formula one says that is simply the product of these two events, right? That means the probability of finding, the first card king, then you need to multiply this with the probability of second card king, right? Okay, so now you have to treat these two as separate problems. You are drawing a card that should be a king. That is, what's the probability then? There are four kings in the card pack out of 52, right? The second time also you will have 52 cards now. You are replacing, remember? So again, I will have, four kings, right? Out of 52. So it is 4 over 52. So simplify this guy. So this should give you how much? 1 over 116. Okay. So that is actually my first part. The second part is finding what? Neither card is a king, neither, neither a card is a king. So that means what? That means in both ways you are getting non-king. Okay, so both cards are non-king. So therefore, the first is a non-king, and the second is a non-king. Okay, so now this is my event E, and this is my event F. So this is independent event, therefore this is just the product of these two. So that is the product of the probability of first card is non-king, and the second one also non-king. So let's look at the first piece, the probability of getting non-king. So there are 48 of them, right? So there are 48 of them out of 52. Right? Second time also you will have the same number of non-king out of 52. Okay, remember you are replacing. So if you simplify that, that should be how much? It should be 144 over 169, right? So those are the two things you have here. Okay, good. So now let's move to the next one, number 8. A student is taking a quiz with 5 multiple choice questions, each question having 4 choices, right? Only one is correct. The student did not study at all and they decides to guess each answer, right? So typically he or she is going to do 5 problems, so student is going to guess the answer, right? Only one answer is going to correct out of 4 choices for each problem. So the question is now first part. What is the student, or what is the probability that the student will guess all 5 correctly? Okay, so again, you know, guessing the answer for one problem will not affect the other, right? Because all 5 problems are separate problems. We have to guess for each problem separately, and therefore, those 5 problems are now considered like independent questions. Therefore, these 5 events are going to be independent events, right? Therefore, the question is finding all 5 correct. So, the probability of all 5 correct means what? Actually, you need to have the first one correct and the second one correct and so on, right? Therefore, the probability of finding first correct and second correct and third correct is going to be the product of, right? The product of, the first problem is getting correct. So this is the first problem is getting correct, right? So you are given 4 chances, so 4 choices, so you have to choose one. So guessing correctly is 1 out of 4. For the second one, also the same thing. So guessing correct for all 5 is, 1/4, 1/4, and so on. Therefore, you need to simply multiply all 5, the correct probabilities to get all 5 correct there. That is why which is 1 over 1024. Okay. Again, the next one, that's going to be very easy now once you understand the first part. What is the probability that the student will guess all 5 answers incorrectly? Again, all 5 questions are independent, so you have to, product all 5 one by one. So getting correct answer for each problem is 1/4. Therefore, the incorrect is going to be 3/4. Remaining all 3 are going to be wrong answers, right? For each problem. So therefore, it is 3 over 4. Getting wrong for the first one, then second one, and so on. So these are the all 5 wrong probabilities. So you have to multiply them to get all 5 wrong. So it is 243 over 1024. Okay. So I'm leaving now. What? Number 9. No, I'm leaving number 10. Okay. So you need to try number 10. But number 9 is the probability that a person is afraid of a thunderstorm is 0.35. If we ask 3 random people, what is the probability that all 3 will be afraid of thunderstorm? Remember asking question for all 3. 3 people are now independent, right? So I'm asking question, they are giving answer independently. Therefore, you need to, multiply all 3 to get all 3 be afraid of the thunderstorm. So that's why we multiply all 3. So the first one is the first guy afraid. This is the second guy afraid, and the third one afraid of a thunderstorm. Simply multiply the probability of being afraid, so which is 0.35. So we are simply multiplying all 3. Okay. Okay then. So I need to discuss number 11 next time. So why don't you think about number 11 when you come for the next class?